and get going. 7.2 is about sample proportions. It tells you what you should learn through the end. So what proportion of U.S. teens know that 1492 was the year in which Columbus discovered America? A Gallup poll found that 210 out of a random sample of 501 American teens aged 13 to 17 know this historically important date. This sample proportion, this is not hard, 210 out of 501 is the statistic. So we talked about statistics and parameters in 7.1. So this is the statistic that we use to gain information about the unknown population proportion P. Because another random sample of 501 teens would likely result in a different estimate, we can only say that about 42% of U.S. teenagers know that Columbus discovered America in 1942. It should be 1492. I don't know why I keep doing that, and I typed it. Man, I typed these notes like 3 years ago. I gotta fix them. I can't find this one. I don't know where it's at. In this section, we use sampling distributions to clarify what about means. So how good is the statistic p hat as an estimate of the parameter p? To find out, we ask what would happen if we took many samples. The sampling distribution of p hat answers this question. How do we determine the shape, center, and spread? Of a sampling distribution of p hat. Well, somebody should be on time. All right, the activity of the candy machine. Imagine a very large candy machine filled with orange, brown, and yellow candies. When you insert money, the machine dispenses a sample of candies. In this activity, we'll use an applet to investigate the sample-to-sample variability and the proportion of orange candies dispensed by the machine. We are actually not going to use the applet because they did it for us and gave us all these graphs. So here's the candy. We have a p hat of 0.40, if you can read that right there. And then here's your distribution, your sampling distribution, and then it tells you that you have a sampling distribution of 25, and we took 400 samples of 25, okay? So the figure shows one set of possible results from step 4 of the candy machine activity. This is that last step. We took all those SRSs or whatever. All right, let's describe what we see. So we're looking at this right here. What do we see in the shape? This graph right here. What do we see?
Bimodal.
Unimodal. Roughly symmetric. And then I'm going to put this on here just to get started with it. Not that. Possibly normal. So anything that's roughly symmetric, we could try to make normal. Okay, so it could possibly be a normal graph. All right. So what is your center? Look at your graph, it tells you. Say it again. Nope, look at your graph. It literally tells you what your center is.
0.449.
How'd you get that?
It just says it.
Yeah, that's what I'm saying. It literally says it. The mean, it's okay. It's 0.449. So if we use the mean for the center, what do we have to use for the spread? Come on, guys. Standard deviation. And it literally tells you that the standard deviation is 0.105.
Can you move your paper down a little bit?
It had to be Mackenzie. It's always Mackenzie. Move your paper. It's hot in here. Are y'all hot in here? It's cold in the hall. Oh my gosh. Yeah. I'm never hot. Yes. All right. The dot plot is the approximate sampling distribution of p hat. If we took all possible SRSs of n equals 25, so that means 25 candies we pulled out of this machine and then we put them back in and then we did it 400 times from the machine and graph the value of p hat for each sample, then we'd have a sampling distribution of p hat. We can get an idea of the shape, center, and spread from the figure above. So sampling candies, the effect of N and P on shape, center, and spread. So what is N? What do you mean the number? Sample size, right? So N is sample size. What is P? Yes. So it's how many, like if we're deciding about orange, they may say that there's approximately 40% orange. That would be our P. What is your proportion? All right. So in a similar way, we can explore the sampling distribution of P hat. When N equals 50, which is step 5 of the activity, you guys can go back and read that activity. It's not a big deal. It's the same thing that I just told you. We take samples of candies. I didn't do that. It's hard for us to do that in COVID. You know, I ain't trying to be mean, but we ain't trying to spread it around or anything. We are going to do an activity. The 3 that are here for A day have already done it, and I wrote all their results on the board. And then you guys are going to do it today when we finish our notes. Okay. So what I want you to do is you'll hand sanitize, pull chips. Once you're done, re-sanitize, pass them over. Does that make sense? And y'all just go around the room. I'll explain it more in just a few minutes, okay? All right. As the figure below shows, the dot plot is once again roughly symmetrical. Okay. So this is the ones at the bottom it's talking about. And somewhat bell-shaped. Remember, bell-shaped is the ones that we like to call normal. The graph is also centered about 0.45. Now, these are little teeny tiny graphs. I'm going to pull it up for a minute. So we're talking about this one. If you look in your book, exactly where this is at, it'll show you down a little bit larger. But it's telling you in here, this is sample size 25. This one is your sample size 50. Okay. So this is the one we looked at a minute ago, and this is the one we're looking at now. Okay. With samples of size 50, however, there is less spread. What did we talk about yesterday, day before, Tuesday, about spread and the sample size? The bigger the sample size, the less the variability, right? Okay, so remember that. In the values of the p hat, the standard deviation in the figure is 0.070. For the samples of size 25, the standard deviation was, remember, 0.105. So we decreased that variability. To repeat what we said earlier, which I already have said, larger samples give the sampling distribution a smaller spread. And again, it says see the figure in the book, which is again repeated down here, so it doesn't matter. What if the actual proportion of orange candies in the machine were 0.15? Okay, so now we're changing it. It was 40. So it was 40%. Now we're changing it at 15%. Okay, the next figure shows the approximate sampling distribution of p hat when n equals 25. Notice that the dot plot is slightly right skewed. And again, these are in the book. It's not a big deal. The graph is centered close to the population parameter, which is 0.15. So when it was 40%, we were close to that 40%. Now we changed it to 15, so the mean will be closer to 15%. That's all it's saying. All right. As for the spread, it's similar to the standard deviation in the first figure where n equals 50 and p equals 0.45. If we increase the sample size to n equals 50, so if we take it from 25 to 50, the sampling distribution of p hat should show less variability. The standard deviation in the last figure confirms this. Note that we can't just visually compare the graphs because the horizontal scales are different. The dot plot is more symmetrical than the graph in the first figure and is once again centered at the value that is close to 0.15. All right, so let's go over what happens with n. As n gets larger, what happens? Come on, guys. Thank you. Variability decreases. What happens as your proportion changes? What will change? Not your sample size. What changes? When we changed it from 0.40 or 0.45 to 0.15, what changed? You're writing and not listening. Where was our graph centered when we were at 0.40? Where was our last mean? The one we described. Where's our mean at? 0.445. I just can't hear you. So we were at 0.40. Our mean was at 0.445. Tell me real quick how I could make that more accurate. How could I make that? Because we said that there were whatever color we were looking at. Let's say we're looking at orange. 40% of the candies in there were orange, but our mean showed 44% or 45%. How can we get a little bit closer? Say what? No. Okay, listen carefully. You ready? Increasing sample size decreases variability. Got that? Taking more samples, so we took 400 in the beginning. Let's say we take 500, 600, 700, 800, is going to push that to that 0.4. So remember, the more samples that we have, the more it's going to push it to the actual probability. Okay, that's what we're trying to get at. Remember, probability is something over many, many times. You don't flip a coin and get 50% the very first time. You might get 100% or you might get 0. It's over many flips. So you guys remember that. All right. So if we change our sample size, that's going to squish our graph together. If we take more samples, that's going to push our mean to what our proportion is supposed to be. Our sample mean should be close to our proportion. Got it? All right. So if we change the proportion, the only thing that's going to change is where the center is on the graph. So if it's at 0.40, we should see our peak at 0.40. If we change our proportion to 0.15, where should we start seeing our peak? 0.15. So does that make sense? So n, making n bigger reduces variability. Taking more sample sizes or more samples gets us closer to our probability that we're looking for. And changing our probability just changes our mean. Okay, so that's the effects of n and p. So what have we learned so far about the sampling distribution of p hat? So the shape. In some cases, the p hat sampling distribution can be approximated by a normal curve. You remember the last chapter when we were doing binomial and geometric and we were trying to switch it to normal? That's the same thing that they're trying to do now. So we're going to try to make everything normal so that we can use normal CDF and all of that. We don't have to worry about anything crazy. The center of P hat should be where? What did I say? Where was the center at? Or what is our ultimate goal? Say it loud. To be, what do we want our mean to be? I didn't hear what you said. Your proportion. But that will only happen as long as P hat is an unbiased estimator. And then what happens to our spread? What changes it? The sample size. So as n gets larger, the variability gets smaller, or the spread gets smaller. If n is small, the variability is going to be big. It's offset. So for a specific value, of P, the standard deviation of P hat, remember that's the population standard deviation of P hat, gets smaller as n gets larger. And then in general, the population standard deviation of P hat depends fully on P and N, your proportion and your sample size. All right. To sort out the details of shape and spread, we need to make an important connection between the sample proportion P hat and the number of successes X in the sample. In the candy machine example, we started by taking repeated SRSs of 25, n equals 25, from a population with proportion of 0.45. So again, we have that 0.445, so we were really close with that. For any such sample, we can think of each candy that comes out of the machine as a trial of this chance process. A success occurs when we get an orange candy. Let X equal the number of orange candies obtained. As long as the number of candies in the machine is very large, X will have a close to binomial distribution with n equal to 25 and P equal to 0.45. The sample proportion of successes is closely, should say, related to X. And this is how. So P hat is equal to the count of successes in the sample, which we call X, divided by the sample size. You already knew this. This is not a secret. We just did that a minute ago when we talked about the teens in Columbus. There were 201 or 210 out of 501. That's what you did. Okay, so don't make this seem more complicated than what it is. How many teens said yes, they knew? 210. How many total were they? What was our sample size? 501. So don't make it too complicated. How is the sampling distribution of P hat related to the binomial count X? From chapter 6, we know that the mean and standard deviation of a binomial random variable R What was that formula for the mean of x for a binomial? See if anybody remembers. Remember that we have n and p. It was just NP. It was just NP. Don't freak out. You get that formula on your formula sheet. Okay? You get that formula on your formula sheet. Do you remember what your standard deviation was? Wait, what? Nope. Y'all are together. Go ahead. 1 minus p. Good. Remember, it's the sample size times the proportion times like your number of successes, number of fails. Okay? So make sure you remember those formulas. This is why I didn't like Christmas break. Y'all understand what I'm saying? Like it's hard to leave and then come back to this, okay? So because p hat formula is x over n, we can rewrite that. So think about it this way. I'm gonna put it over here just so you guys can see it because these are both letters. If I had an equation that I had x over 2, I could rewrite it as x times 1/2. Y'all understand what I'm saying? Or 1/2 x. Y'all see that? That's what I'm about to do right here. I can rewrite this as x times 1 over n. So I wanted to kind of relate it so that you guys could see it because sometimes just using variables is really hard. We are just multiplying the random variable x by a constant 1/n to get the random variable p hat. Recall from chapter 6, I know that's been a while, that multiplying by a constant multiplies both the mean and standard deviation. So remember when we multiply, it affects everything. What about adding, subtracting? Nope. Just affects the what? Mean. It's just the mean. Yeah, same thing. The same thing. So it just affects the center is what we're talking about. So you're not wrong in what you said. So remember, when you multiply, you're going to affect everything. When you add or subtract, you're just moving it left or right. You're not changing how fat or skinny it is. You're just moving it left to right by adding or subtracting. So the only thing that changes is where the center is located. So remember those rules as well. And we've been doing those rules for a few chapters now. Okay. So what does multiply affect? Yep, the center and the spread. And then add and subtract only affects center. What affects the shape? Nothing. Okay, y'all got that? All right. So then we have the mean of p hat. This is just deriving the formula. So if you don't understand, I'm going to try to explain the best that I can. If you don't understand it, just know the formula. Okay. We're going to have the constant 1 over n times our formula for mean. What happens when you multiply 1/n and n? What happens when you multiply 1/2 and 2?
It just cancel out.
Yeah,
Go on.
yeah, it just goes away. So we're just left with p. This confirms that p hat is an unbiased estimator. All right, so same thing with our standard deviation. If we decide to multiply it by some factor, we're going to multiply 1 over n times the square root of n p 1 minus p. This is the hard one to follow. This is the hard one to follow. I want to put this 1/n back in there. 1/n back in there. So the way I put it back in there is by doing n over n squared. N over n squared. Okay. Then we have our P, just the n squared is basically what's coming out. If you guys look at it like this, if we took the square root of 1/4, the square root of 1/4, the square root of 4 is 2. So we just have that 1/2. So you take the square root of the top, the square root of the bottom. And then whatever else is left in here, like if you had the x, it would go back inside. Okay. So that's exactly what we're doing here. Sorry, this should be parenthesis 1 minus p. When we're doing fractions and we have the same on the top and the bottom, we can cancel it out. So the square will cancel out. And this formula becomes p times 1 minus p over n. Again, these are just deriving formulas. So if you've had calculus, you've probably derived some stuff. If you have not, and you're going to take calculus, you'll probably see this again. Okay, so don't stress out too much. All you need to know is that the mean is going to be p, and the standard deviation is going to be this formula right here. All the stuff in the middle is just how it got that way. Okay? That takes care of center and spread. Struggling. You good? Let them germs off. What about shape? Multiplying a random variable by a constant doesn't change the shape. We just talked about that. So the sampling distribution of p hat will have the same shape as the distribution of the binomial random variable x. So the shape does not change. Have a great day. If you study the optional material in chapter 6 about the normal approximation to a binomial distribution, then you already know the punchline. Whenever NP and N1 minus P are at least a 10, a normal distribution can be used to approximate the sampling distribution of P. And we did that. So remember that we tried to decide whether we could use normal or not. So we went from binomial and then tested it N and 1 minus N, sorry, NP, and then N1 minus P to see if it made 10. And if it did, we could use that normal instead of doing binomial. All right. The figure below displays the facts in a form that helps you recall the big idea of a sampling distribution. The mean of the sampling distribution of p hat is the true value of the population proportion p. The standard deviation of p hat will get smaller as the sample size increases. So again, you increase sample size, you decrease variation. In fact, because the sample size n is under the square root sign, we have to take a sample 4 times as large to cut the standard deviation in half. So just what I showed you, if you wanted to get 1/2, you would have to multiply it by that 4. That 4 has to go on the bottom to be able to pull out that square root to be a half. Okay. That's not super important. It's just showing you why it says 4 times as large. All right. The two conditions in the preceding box are very important. So the large counts condition we've already talked about. If we assume that the sampling distribution p hat is approximately normal when it's not, our calculations will be flawed. And those calculations are that NP and N1 minus P have to be greater than or equal to 10. That was one of the last things that we did. The 10% condition we did when it failed, what can I think? Ben, yeah, when it failed Ben's. Independence, sorry, like I. When it failed independence. Okay, so remember when we said it wasn't independence or we didn't know if it was independent or not, then we made sure that we did the 10% condition. So we use this when we were not replacing. Or not independent. To help assume normality. If we sample too large, calculations will be flawed. So don't forget those, sorry y'all, don't forget those two rules, the 10% condition. We actually learned the 10% condition first, so I don't like that they put these out of order, but we learned the 10% condition first in bins. And then after we got through bins, we had to check our large counts condition to make sure that we could do the normal approximation instead of doing binomial or geometric or anything like that. Okay, so that's all that's about. When we are sampling without replacement from a finite population, the observations are not independent because knowing the outcome of one trial helps us predict the outcome of future. So what does that mean? Give me an example of that. Give me an example of a finite population where the observations are not independent.
Have like 5 pieces of red candy and 5 pieces of brown candy, and you pull a red one out and eat it, and then you draw again.
Yes. An easier one would be drawing from a deck of cards and not replacing. Does that make sense? He's absolutely right. It's anything that you don't replace, because what do you do when you don't replace? You change the probability. You change the probability. So remember, in all these, we want that constant probability. So to get from that non-replacement, we have to do that 10% condition, and then we have to do our large counts to assure that we have normality. All right. But the standard deviation formula assumes that the observations are independent. If we sample too large, which is why we do the large counts, a fraction of the population, our calculated value of the standard deviation will be inaccurate. Because larger random samples give better information, it sometimes makes sense to sample more than 10% of the population. In such a case, there's a more accurate formula for calculating the standard deviation of p hat. It uses something called a finite population correction. But we're not doing those, and you won't do those. Okay. All right, so check your understanding. About 75% of young adult internet users that use 18 to 29 watch online videos. Suppose that a sample survey contacts an SRS of 1,000 young adult internet users and calculates the proportion p hat in this sample to watch online videos. What is the mean of the sampling distribution of p hat? So we're going to talk about number 1 first. How do I find the mean of the sampling distribution? We just learned that formula. What was it? Look one more time.
Just P.
Just P. Just P. What was just P? What does P represent? Proportion. What was our proportion? 75%. So remember again, population, proportion is the same thing as the sampling distribution. Find the standard deviation of the sampling distribution of p hat. Check that the 10% condition is met. This is a crazy question. You have to check the 10% before you can take standard deviation. Okay, check the 10% before the standard deviation. So remember that's 10 times your sample size. Which gives us 10,000. Remember the question that you ask, is there more than this in the population? Is there more than 10,000 18 to 29-year-old users? What do you think? Is there more than 10,000? Absolutely. Absolutely. Put it in perspective, there's probably 10,000 probably at a college, a big college. You see what I'm saying? 18 to 29, there's a lot of people. Y'all understand what I'm saying? All right. So this would be in one little tiny area. We're talking about all of them. So 10% condition is met. So then what is the new standard deviation formula that we have talked about? So remember the top is P, 1 minus P, fails and successes over the sample size, and then take the square root. What was our proportion? 0.75. So that means our fail would be 0.25. What was our sample size again? Yep. Y'all got it. Have some confidence. Y'all are not doing bad today. It's just a lot of remembering. Okay. We'll get there. When we put this in our calculator, and I'm not going to make you do it, you get 0.0137. So that's your standard deviation. This is just helping you remember what the 10% rule was, and then making sure you know the new formula for standard deviation. That's all. So the next one says, is the sampling distribution of p hat approximately normal? So this could have been a binomial. It's probably going to be a binomial. We want to make it normal so we can use normal CDF or normal PDF. Got it? So the way we decide whether it's normal or not is we check the large counts. The way we do that is NP and N1 minus P. And they both should be what? Bigger than what? I already wrote it one time, I think. Not on this page, but 10. Yeah, bigger than 10. Don't stress out. Answer. If you're wrong, you're wrong. If you're right, you look even better. You know what I'm saying? Like, don't stress out. So they have to be bigger than 10. So we do 1,000 times our percentage or our proportion. We get 750. We also do 1,000 times 0.25, which gives us 250, which is greater than or equal to 10. So it passes the large counts. So what can we say about this? It's approximately normal. When can you say that it is normal? Kind of a trick question. When they tell you, it'll say, this is a normal distribution. Got it? You got it? So when they say check for normality, approximately normal. Okay. All right. Number 4, if the sample size were 9,000 rather than 1,000, how would this change the sampling distribution of p hat? So how would it change the shape? I'm going kind of backwards. Shape. How would it change the shape? Shape. Is it going to be left skewed, right skewed, or normal? You understand what I'm saying? So if I go from 1,000 to 9,000, what's going to happen to the shape? Thank you. Nothing ever happens to the shape. It's going to be approximately normal. Don't stress out, it's okay. It's hard to go from talking about center and spread and making shape that last one when you're changing it to then going back to shape, center, spread. So don't stress out, it's okay. What about your center? What happens to your center when you increase? Think about what the center is when you increase from 1,000 to 9,000. Think about it. Wow, what is your center? The proportion. Did we change the proportion? No. What is changing the sample size going to do? Make it more towards that center, right? So this is not going to change either. We just know that it's still going to be at 0.75. Now, what's going to happen to the spread? Okay, but we have to talk about how it gets smaller, and you need to pay attention to this one. Remember that one little blurb where it says you have to do 4 times as much. So if you wanted to get 2, you have to do 4 times as much. Y'all see what I'm saying? Y'all remember that little blurb I told you and I showed you the 1/4, whatever. All right, so this is it. So what's going to happen to your spread? Our spread is calculated by P, 1 minus P over N, take the square root. This time, we still have the 0.75 and the 0.25, but now we have 9,000. When we put this in our calculator, it gives us 0.0046. What did you do to 1,000 to get to 9,000? What did you do? Multiply by 9, right? So if we do this, let me show you really quick. What is the square root of 9? 3. This is 3 times different. Okay, 3 times different. So that's different from this 0.0137 that we had up here for 1,000. So that's going to be your difference in those. All right, we're going to flip it. All right, we have this and one example and we're done, okay? So I know it's going a little bit longer than an hour, but we're going to get there. Inference about a population proportion P is based on the sampling distribution of P hat. When the sample size is large enough for NP and N1 minus P to both be at least 10, remember that's our large counts rule, the sampling distribution of P hat is approximately normal. So large counts tells us that it's normal. In that case, we can use a normal distribution to calculate the probability of obtaining an SRS in which P hat lies in a specified interval of values. So here's an example. This is a full page example, state plan, do, conclude, okay? And then we're done. Everybody good? All right. Normal calculation involving P hat. A polling organization asks an SRS of 1,500 first-year college students how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of this true value, and show your work. So when we do our state, we want to talk about what we do know. What did they tell us in this paragraph? Okay, so our proportion is? Our proportion is also equal to our what? What else can we call it? Our mean. What else did they give us? Think about all our formulas we had. We got to have what? Yeah, but how do we get standard deviation? What do we need to be able to plug in that formula? N. We have P, right? Now we need N. What is N? Perfect. You need to define those at some place. Then remember, they're asking, find the probability. So remember, we're going to make one of those probability statements that gives a result within 2 percentage points of this true value. So what's our true value? 0.35, right? So within 2, does that mean 2 over or 2 under? Either. So how do I write that? Perfect. Less than or equal to P hat, less than or equal to 0.37. So 2 below and 2 above. Perfect. So that's what we have and what we want to do. We're going to make a plan. We're going to make a plan. We have to be able to calculate it normal. It wants you to do it normal, CDF. What do I need to do first? What do I need in that normal CDF?
Standard deviation.
Standard deviation. What else do I need? Normal CDF, I do what? What comes first? You do need the mean. So that's your other one. Upper and lower, right? Okay, so we're going to talk about all that. But you did fine. You did fine. Why are y'all so stressed out about it? Was it you?
Yeah.
I thought it was her. I can't see your mouth moves. It just sounded like it came from her. Okay, sorry. All right, so what do we have to do though? To be able to take the standard deviation or to calculate the standard deviation, what do we have to do first? Check what? What I tell you comes first. 10% rule. So check 10%. How do we check the 10%? Yeah, that's it. What thing do we do? Nope, not on this one. You're thinking about large counts. 10% rule. What do we have to have 10% of? The population. So how do I do that? Not the times the population, but times the sample. Our sample is 1,500. No, y'all are perfect. You'll remember it if I make you answer it. So what's this 1,500? What are we trying to see? The question we ask, are there more than 15,000 first-year college students in the population? It said a polling organization asked an SRS of 1,500 first-year college students how far away their home is. So do you think that in the U.S. that there are more than 15,000 college students? Yes. So now that we check this, what can we do? Find the standard deviation. What's that formula for the standard deviation? Success, fail, success, fail. So perfect. Well, I'll get it together. That's okay. It's okay. It's okay. What's your P? Shh, shh, shh. What's your P? 0.35. So 1 minus P would be? What's our N? 1500. When we calculate that, we get our standard deviation is 0.0123. We need to check to see if it's normal. And we do that by the large counts. What are those formulas? NP and then 1 minus P. So N was 1500, our P was 0.35, and our 1 minus P was 0.65. We get 525 and 975. What are we making sure these numbers are? They're both greater than or equal to 10. They have to be bigger than 10. If they're less than 10, then we can't assume normality. If they're less than 10, we cannot use normal CDF. So there's your state and your plan. Now we have our do. So we said, yes, it passes the large count, so we can assume that it is approximately normal. So we can do normal by CDF. Remember, PDF is perfect, equal. CDF is not equal, so it'd be less thans or greater thans. Okay, so think about that. PDF is perfect, equal to exactly. All right, what would our lower be? Think back to what we're trying to find, our proportion. 0.33. What's our upper going to be? What's our mean? We calculated that. We really didn't calculate it, but good, 0.35. And our standard deviation we found was perfect. When we put that in our calculator, I'm going to go ahead and tell you, you get 0.8961. And then you need to tell me what that is, so we conclude. What were we trying to find? It said find the probability that. Not 35%. Okay, so 89.61% of all SRSs of size 1500 will give results. Just stated exactly what the problem did. Within 2 percentage points of the true value. That's it. Okay. All right. Nobody go, nobody leave Zoom. I'm going to stop sharing, stop recording.